Alright, this video is going to go over graphing phase portraits for linear constant coefficient systems of differential equations. Now the system of differential equation has an x and a y component to it in a vector form. So when we draw the phase portrait for it, the phase portrait is going to be usually x on the horizontal axis, y on the vertical, kind of like normal, but what's different about these is that for each different solution trajectory, so for the solution curve, we're going to have an arrow, and that represents the time variable involved in all of this. There's lots of different graphs. It basically breaks down into 3 different ways to graph, and they're different depending on whether there are 2 real eigenvalues, a repeated eigenvalue, or complex eigenvalue. And then those different parts depend on whether the eigenvalues are, well, for the 2 real, if they're both negative, we get a different kind of a graph from if they're both positive, versus if one is negative and one is positive. For the repeated eigenvalue, we're only going to look at what happens when they're positive and negative. It's called doubly degenerate when they are both 0, and we're not going to look at that case. Complex eigenvalues, for these we only need to look at the real part, since that's what the exponential is raised to, and that will tell us stuff about the system, and we'll get there in just a second, but that's dependent on whether it's positive, negative, or 0, just the real part. The complex part also tells us that it spirals because it oscillates, but the real part gives us a lot more information about the graph. Okay, here we go. So let's do the real eigenvalues first. All right, here are 3 different matrices that would be associated with a system of differential equations. Their eigenvalues for each one and eigenvectors for each one. So you'll probably have to pause this video each different time we go through these, just so that you can write down the matrix and its associated eigenvalues and eigenvectors. So this is the information. It's the basic information we need. Actually, all we need is the eigenvalues and eigenvectors to graph each one of these things. So notice this is the case where they're all real eigenvalues. On this first one here, that's an equals, not a negative. Both of those eigenvalues are positive. On the second one, both eigenvalues are negative, and on the third one, there's one positive and one negative, and you'll see how this will affect each different system. Okay, so for the first one, and what we're going to do for every single one of these, is look at the eigenvector and graph a vector that goes in the direction of that eigenvector. Okay, so it goes 2 in the x and 1 in the y. So x and y. That eigenvector goes 2 in the x, 1 in the y. So there's a point. I just went from 0, 0 to 2, 1, and I'm going to draw a line through that point in both directions. And so that is a vector in the direction of 2, 1. Now because the eigenvalue is positive, that means all solutions on this line would trend away from the origin. And I need to write down that lambda is equal to 1. I need that for later. So I graphed the eigenvector, put arrows on it to show that all solutions go away from the origin, and that's because 1 is positive. Right here, this 1 is positive. And then I marked it with which eigenvalue it was. I'm going to do the same thing for that eigenvalue of 3. The eigenvector is 1, 1. So there's a dot at 1, 1, and I'm going to draw a line. Wow, this is hard on this on this thing. That goes through the origin. It does. Just pretend. This is hard to graph these. Okay, so there's that line. Sorry, I'm going to back up and see if will it actually back up. It won't. Can I erase because that looks horrible? Okay, I'm going to try again. See if I could actually draw a line on this thing. All right, so through 1, 1. Okay, better. At least through the origin this time. All right, so now that one had a positive eigenvalue again, so positive arrows going away from the origin. There they are, going away. And that one goes with lambda equals 3. Okay, now all arrows are pointing away from the origin. And what this means is that all solutions are going to point away from the origin. So I'm going to start, and I'm going to start right here, near the origin. And I know that as time goes to infinity, e to the 3 is going to be way bigger. So here's my thought process, is that e to the 3t is going to be way bigger than e to the t as time goes to infinity. And what that means is that all solutions are going to look like this eigenvalue as time goes to infinity, which means that they're starting out looking like the other one. So I'm going to start at the small eigenvalue or eigenvector and trend towards the big. So notice I made it look parallel to the big one. So now I'm going to come over to this region. I'm going to draw another solution that's sort of representative in there, but I need to start being parallel to the small one. So I'm trying to figure out which one is the small one here. That's that one. And then it's going to become parallel to the big one as time goes to infinity. Now, just like before, when solutions went away from an equilibrium point, it was called unstable. It's the same here. So this would be classified as unstable. All right. I'm not going to draw solutions in this portion and this portion. Well, let me just draw one, and you can see why I wouldn't in general, because they sort of look funny. So if I start being parallel to 1 and then become parallel to 3, you can sort of see it just looks a little bit strange. I guess I'll draw it in there just so that you can, yeah. It looks a little bit strange. So depending on how close the eigenvectors are together, I might not draw solutions in between them if they're too close. Okay, on to the next one. Same exact process. Now this one has negative eigenvalues, which means that instead of arrows going away from, they're going to go into. So for the first one, the eigenvector was 1, negative 3. So I'm going to go to 1, negative 1, 2, 3, about there, and attempt to draw a line through the origin and through that point. Okay, and that one was associated with negative 3, and it's negative, so arrows go in. The next eigenvector is 0, 1. That means I go nothing in the x and up 1 in the y, and then draw a line through that in the origin. So really this is just the y-axis. And again, eigenvalue is negative, so solutions go in. And that one was associated with y equals negative 2. Now the rest of the solutions are different. The one on the left, I started at the origin because all solutions sort of start at the origin and work their way out. Now on this one, all solutions end at the origin, so I need to start away from the origin and then work in. And I need to start away from the origin, parallel to the smaller eigenvalue, and then get close to the big one. So let's see, the smaller one is negative 3, so I'm going to start away from the origin and parallel to negative 3 like that. Away from the origin, parallel to negative 3, and then I'm going to become parallel to the big one as this works into the origin. All right, same thing kind of over here on the left. I've got to figure out which one is negative 3, go parallel to that one, and then as it comes into the origin, it's going to swoop parallel to the one that was negative 2. All right, and again, I'm not going to draw them in between those two because they're so close together. It makes it look just a little silly. Now this one, all solutions go into the origin, so this one is called stable. All right, next one, vector is 5, 2, so I'm going to go over 5, up 2, and draw a line, there we go, parallel to, or through 5, 2. Now that one went with a positive eigenvalue of 4, so solutions go away because that's positive. And then the next one was 0, 1, so 0 in the x, 1 in the y, that's again the y-axis, and on that one solutions are negative. So arrows go in, and that's because the eigenvalue was negative, of negative 1. Now, this is called a saddle. And these are a little bit easier to draw because you don't have to think about which one's bigger and smaller. You can follow the arrows because the solutions do not tend towards nor away from the origin. They do neither. So I just follow the direction of the arrows. So up here on the left, I've got arrow going down, arrow going left. So solutions in that portion of it are going to go down and left. Upper right, solutions go down and right, so down and right. Lower right, solutions go up and right. And lower left, solutions go up and left. So that's what a saddle would look like. Oops. Page. All right, so here are two different systems with a single real eigenvalue, so repeated eigenvalues. Now the process of graphing these starts out very similar, where you look at the eigenvector. So in this first one, the vector is 3, -1, and then you draw a line 3, -1, and draw a line sort of through 3, -1. The eigenvalue is positive, so all solutions tend away from the origin. And now the trick is we don't know which way the solutions go from here. Because if you look up above that line, solutions are going to start at the origin and work their way out because everything's going away because of that positive eigenvalue. And they're either going to trend clockwise or counterclockwise. Now, the way that I do this is I'm just going to pick a random point. Now, I like the point 1, 0. That's like right over here on the x-axis. So it's a nice point to pick. Now, if I multiply that by a, then what I get is a vector. So that would be the vector 2 times 1 is 2, plus 0 is 2, and 1 times a third is a third, plus 0, so that's a third. And so I get a vector, and so from the point 1, 0, this tells me that a vector goes in the direction 2, a third, so there's like a little tiny arrow going in that direction from 1, 0. So, wow, that is really hard to tell. I don't like that arrow. I can't tell whether these are going clockwise or counterclockwise from it. I'm going to pick a new point. 2, -3, 1/3, 4. Let's try 0, 1, another one that I like. Just because the zeros make it pretty easy. So that would be a vector. That would be in the direction of -3 and 4. So I'm going to go to 0, 1. That's up here. Go in the direction of -3 in the x, +4 in the y, so that's up that way. Okay, so that arrow is a little bit better. And what it tells me is that solutions are going to become parallel to that left-hand arrow. Or kind of looks sort of like it. So I'm going to go, then it also tells me that these go, let's see, which direction is that? That is counterclockwise. So counterclockwise there. You can kind of see how my arrow matches up there. So solutions in the other direction go the opposite way. So once I've got one of these, I can fill in the other by going the opposite direction. Okay, let's look at this next one. By the way, these are all going out again, so that would be unstable. And so in this other one, vector is 1, 2. So there's a line that's approximately 1 over in the x and 2 up in the y. Now everything is negative on this one. That's because of that -5. I need direction, so I'm going to take A and multiply it by, let's go for the 1, 0, see if that works out for us. That's a 3 right there. So 1, 0 would give us -7, -4. So if I go to 1, 0, that's -7 in the x, let's see, negative 7 in the x, negative 4 in the y. And solutions need to trend towards the origin. So in order to follow that arrow, they would have to start here, go through that arrow, and then become parallel to the other one. And that means that solutions are going to do the opposite on the other side, and again trend towards the origin. And this one, because they all trend into the origin, this one is called stable. All right. Whoops. Okay, so now the complex eigenvalues. Notice there's 3 different scenarios, one where the real part is negative, one where the real part is positive, and one where the real part is 0, and this is the part of the eigenvalue. So all that's needed on these is the eigenvalue. You don't need the eigenvector because you get cosine and sine. These actually spiral, so you get circular patterns with this. Now, the negative 2 here says that we're going to go into the origin. So just like the negatives before, this would be stable, but it's going to spiral. And so we know it's going to go into the origin, but we need to figure whether it does that clockwise or counterclockwise. And the way to figure that out is to do the exact same thing we did with the real ones, which is to take the matrix, multiply it by a random point. I like 1, 0. So when you multiply this, you get negative 2 plus 0, 0, and negative 3 plus 0, 0. So then I go to the point 1, 0, and then I graph an arrow approximately in the direction of negative 2, negative 3. And so if I follow that arrow, that leads me clockwise. So I know that these solutions are going to go clockwise and into the origin, like that. So there's just one, and I'm going to draw a couple arrows pointing into the origin. I could draw more than one, but one is sufficient. All right, on this next one, notice that the eigenvalue is positive. All solutions are going to go away from the origin, and we've been calling away from the origin unstable. And to specify that this is a little bit different than the other ones, we're going to say it's an unstable spiral. And again, I need direction, so I'm going to take that matrix, multiply it by 1, 0, my favorite point, and get to negative 3. So I go to the point 1, 0, draw an arrow in the direction of 2, negative 3, and if I keep following that arrow, that is also going to be going clockwise. And so I can draw a solution that's going to start at the origin and go clockwise and away. Did I get arrows pointing away? Yes, from the origin. Okay, the next one, there is a 0 here, which means that solutions do not go into or away from the origin. And so this is called a center. Sorry, I was just about to write a spiral, but it is called a center when solutions go neither into nor away from the origin. So these look like circles or ovals. I'm not going to get into the details of the circles or ovals. Those kind of more have to do with the matrix itself and these vectors. So all I need to figure out is direction on this one. I'm going to take that matrix A, multiply it by my favorite 0.10, and get 0, negative 5. So from the 0.10, I'm going to go 0 in the x and negative 5 in the y, so that would just point straight down, and so that tells me, once again, clockwise. It is possible that these go counterclockwise. I picked 3 that went clockwise, not on purpose. Okay, so that would go clockwise like that. So there's one solution. And again, 1 on these is very sufficient to show exactly what would happen with all different types of solutions, any solution trajectory.